Okay, so we're going to talk about center of mass in this video. So we've already talked about center of mass, or at least used that word before when we did rotation. But this represents where the position where the mass of an object or the system can be generalized to a single point. So if you imagine like a large object like a car or truck or something kind of funny shaped, the center of mass is where we can take all the mass and just visualize it at one tiny point, kind of like what we do for a free body diagram. In terms of balancing, it's the point where an object is completely balanced. So there's a couple ways you can find the center of mass experimentally. The first way is kind of easy. You take some kind of fulcrum or balance, like a seesaw, and you put an object on that fulcrum and you move the fulcrum until the object balances. An example would be, think of a meter stick. Okay, so we've got a 1 meter stick, and if you were to take this and use your finger as the fulcrum and rest the meter stick on your finger, you'd find that as long as your finger is at the ½ centimeter mark, then the meter stick would stay balanced on your finger. So that must be where the center of mass is. Okay. Another way to experimentally find center of mass is, it's kind of abstract to think about, but I mean it works, would be take the object, especially if it's misshapen or kind of, the density is not quite uniform, and you just hang it from a string. And once it's in equilibrium, you can draw a vertical line down the object, and then what you would do is turn the object and hang it from a different point, wait for it to go to equilibrium and draw another line, and keep hanging it at different points on the object. And every time you hang it, draw a vertical line straight down. And what you'll end up seeing, kind of just do a quick little visual, like if I hang it from, say, this point over on top, and then I get a straight line once it's in equilibrium. Now, I can't turn the paper, but if I turn the object and hung it from this point in the lower left, then another one on the upper right, then another one on the lower right, and so on, I see all these vertical lines intersecting at a common point. And that would be the center of mass of that misshapen object. So it's an abstract way of doing it, but it is a way nonetheless of figuring out where the center of mass is. Now, the way that we're going to focus on for center of mass is mathematically. Now, the proof to do this is not too bad. You're basically just taking the product of each mass in the system times its location from some origin. You're adding them all together, and then you divide by the total mass of the system. So if we had an example where we had two 1 kilogram masses, so they're the same mass and they're separated by 1 meter, conceptually we know that the center of mass should be at the middle, because everything is balanced across the middle. Well, let's mathematically write it out and determine that. So we'll say mass 1 is on the left and mass 2 is on the right. Now, each x is measured from an origin, so you have to pick that. And you could pick it in the middle, and then one mass is on the negative side, one's on a positive side, but it's usually better to pick the origin at one end of the system. So we'll say that this left mass, mass 1, is located at the position x equals 0. Okay, so 1 kilogram located at the point 0, and then another 1 kilogram located at 1 meter. And there's a total of 2 kilograms in the system. So on top we get 1 kilogram meter divided by 2 kilograms, which gives us our 0.5 meters, which is what we already conceptually knew, but this is how it's mathematically verified. Okay, now if we had a system where maybe the masses were different, maybe there's 3 kilograms on one end and a 1 kilogram mass on the other, we do the same thing. Okay, and so now that the heavier mass is on the right, we should see that the center of mass should be closer to that larger mass. So again, 1 kilogram located at 0, the 3 kilogram mass located at 1 meter. Now there's 4 kilograms in the system, so that means our center of mass is actually 0.75 meters from the left mass. So it is closer to mass 2. So it's an easy concept. We're going to do another example here where we deal with center of mass in 2 dimensions. So imagine we have 4 masses, each separated by 1 meter. So it's a 1 meter square. And let's say the top left mass is 2 kilograms, 3 kilograms bottom left. We'll go 5 kilograms top right, 1 kilogram lower right. And we want to find the center of mass of this whole system. Okay, and I'll label these masses kind of going in a counterclockwise direction. So I'm picking the lower left point to be the origin because I'm thinking like a standard XY coordinate system because that'll be the easiest to use. Okay, so we're going to do the center mass just like the other examples, but this time we're going to split it into X's and Y's. So first, in the X direction, what is the X location of the center of mass? Well, we've got 4 masses to work with, so 4 positions. Now the 3 kilogram mass is located at the origin, so that's 0. The second mass is 1 kilogram located 1 meter away. Now the third mass, the 5 kilogram, is also 1 meter away, because keep in mind we're talking how far on the x-axis. And then mass 4 is on the y-axis, so 0. And the total mass is 11 kilograms. So we'll crunch these numbers out, and we'll get 6 kilogram meters over 11 kilograms, which gives us a center of mass of 0.545 meters. So now that's the location of the X center of mass. So now what about the Y center of mass? Well, we do the same thing, but now we just look at the Y coordinates of these masses. So we've got mass 1 still at the origin. Mass 2 is on the x-axis, so it's nowhere on the y-axis. Mass 3 is now at the position on the y-axis of 1. And mass 4 is also on the y-axis at a position of 1. And the total mass hasn't changed. It's still 11 kilograms. Okay, so let's crunch these out. And now we'll get 7 kilograms meters over 11 total kilograms, which makes our Y center of mass 0.636 meters. Now, we would typically write this out as a coordinate pair because we have our X location and Y location. So the overall center of mass of this system is an ordered pair of X 0.545 meters, comma Y, which is 0.636 meters. And that is our answer. And if we try to diagram this out on the picture, assuming that it's perfectly drawn to scale, we would see that it's not quite in the middle. It's a little bit closer to the 5 kilogram side. So a little more to the right and a little more up.
All right, so for this next part, we're going to show calculations for center of mass when the object has an evenly or somehow it's distributed constant mass. Okay, so we've done problems where the mass or point masses arranged somehow in orientation to each other, but what about if it's just one continuous object? Okay, so we've got to incorporate integration techniques here. Okay, so imagine a stick with a mass spread out throughout the stick. Now, if we calculate center of mass, okay, the formula would be to take each x value and times a mass value, so the mass at that position, for as many masses as there are, and divide it by the total. So that's the generic center of mass formula. Now, because this is a continuous distribution of mass, okay, we can't look at a wholesome amount of mass at each point. Okay, instead, we have to look at a tiny, infinitely small amount of mass located at some point x. So remember, dm, the d represents a very tiny amount of mass m. Okay, which makes it that there's an infinite number of these things inside this stick. So in the numerator, we can then change this summation notation into an integral of x dm. Okay, now on the bottom, it's important to remember that to find the total mass, you're simply doing a integral total of all the little masses. And so this is kind of how our center of mass equation changes when we're talking integrals. Okay, now one of the things we need to talk about before we do any examples is we need to review something about density. Okay, so when we're talking about density, you've seen density in like chemistry or lower level science as mass per volume. Okay, this is the pretty standard way of calculating a density. Okay, now what you probably have not realized is that this formula is dimensionally dependent, which means if you're doing mass per volume, you're talking a three-dimensional space. Okay, because that's what a volume is. It's a three-dimensional object. Okay, what you probably have not done before is look at density in multiple dimensions. So the volume density represents 3 dimensions. There's also an area density, which would be mass per area. So this would be a 2-dimensional density. And then, of course, you would also have a mass per length density, which would represent 1-dimensional. Okay, now each one of these variables, that's kind of important too, so we know the difference. Your density has the Greek symbol rho. It looks like a little p, but it's actually the Greek symbol rho. Then the area density has the Greek symbol sigma, lowercase sigma. And then the length density has the Greek letter lambda. Okay, so again, you've probably not seen these before, but it's important for us in what we do with physics. Okay, when we're talking about center of masses, or in the next video with moment of inertia, it's important to know the difference between linear, mass, and volume densities. Okay, so let's consider the first problem of finding center of mass of a solid object. Okay, so imagine this stick of length L and a total mass M. Okay, and it's important, you'll see this in the problem, and it's a key word that you really have to pay attention to, is we will say that this has a uniform density. Okay, now what a uniform density means is that no matter how much mass you look at, okay, that much mass and the amount of length that comes with it will always be the same overall density, no matter how much mass or how much length you pull. Okay, so linear mass is lambda. That means if I look at the total mass to the total length, that ratio is going to be the same for anything. So if I pick another small amount of mass, there is a small amount of length, that the ratio would be the exact same because it's uniform density. It doesn't matter if I look at the whole stick or a tiny piece of the stick, the density will be the same. That's what we mean when we say uniform. Okay, so in this case, this lower m and lower L, that ratio would be the exact same ratio as all the mass and all the length because it's uniform. Further, if I were to look at an infinitely small amount of mass and an infinitely small amount of length, okay, which I'm going to say x because we're talking in the x-axis here. Okay, this infinitely small amount of mass and infinitely small amount of length is also the same as the total mass to the total length because, again, uniform density. Okay, so understanding the word uniform is important here. So it says that density is constant everywhere throughout this stick. Okay, now what that means is we could take these two, the infinitely small ratio and the total ratio, and set those equal to each other, because what we're trying to do is when you look in our center of mass formula, we have dm's. And that's what we want to get rid of. We want to take those out and put it over an integration variable we can actually do. Okay, so that means I'm going to take these two ratios and I'm going to solve it for dm, which means if I multiply the dx over, I get the total mass over the total length times dx. Now I have something that I could plug in for my integrals. Okay, so let's go ahead and work on this problem. So we'll start by writing out the center of mass equation. Okay, and again, this is for integrals. Okay, and now we'll make some substitutions. Now, the first substitution I want to make is on the bottom. Okay, because since it's a uniform stick and the mass is evenly distributed throughout, then it makes sense to say that the sum of all the little bits of masses is simply equal to the total mass. Okay. Now in the numerator, we'll make a substitution for that dm. Okay, and now you'll notice we have variables we can integrate over, right? The x and the dx. Now m over L is a constant, so I'm going to pull that out. And then all of that is over m, total mass. And then we just have to do the integral of x dx. Okay, and keep in mind the limits. So what are we integrating over? Well, if we start at the left end of the stick, we'll call that 0. Okay, an x value of 0. And then we get all the way to the right end of the stick, which is the value of whatever L is, whatever the length of that stick is. Okay, so we'll calculate this integral. So the first thing is m over L divided by m. We'll cancel out the m, and I'm left with 1 over L. Okay, the integral of x dx is an antiderivative, which would be 1/2 x squared. And then we have to evaluate it between the limits. Okay, now don't forget to evaluate the limits. You plug in the upper limit first, and then subtract the lower limit. Okay, so when I crunch that out, the 0 term disappears. We're left with 1 over L times 1/2 L squared. Cancel out the L's, and you end up with 1/2 the length as your center of mass. Now this should make sense. When we're talking about a uniform object, right, an object with uniform density, it would make sense that the center of mass would be right in the object's center. Okay, so we basically did a lot of calculus work to kind of prove what we intuitively already knew, but this is why when you look at an object of solid mass that has uniform density, we find the center of mass right in the middle. Okay, but what if the density was not uniform? Okay, so before we go into that example, though, I want to hit one other point. If we're talking about an object with uniform density, right, let's say you have a car, and we'll say the car has a uniform density. Now that's oversimplifying it, but let's just visualize that it does. And you've got two people, so these boxes here represent the people. If we wanted to find the center of mass of this whole configuration, one might think you'd have to do integrals because the car has a spread of mass everywhere, and you have to do all the integrals to find its center of mass. But the key is that if we were to make a reference line that's the exact length of the car, okay, you would have these two people kind of sitting in these locations. Then you would have the car. Because it's a uniform object, we automatically can say that the mass of the car is located right in the middle of that length. And so now what you have is a problem that shows 3 different masses located at 3 locations on a reference line. And we could do this problem without any calculus. Okay, so this first example I did was just to show that when it's a uniform object, the center of mass is right in the middle. Okay, and that being the case, if we're 3 people standing on a uniform beam, right? So if you got a metal beam that's going horizontally and 3 people are standing on it, you've got 4 masses, the location of the 3 people, and then the mass of the beam, which is located right in its center because it's a uniform beam. Okay, so that's kind of the idea. Now let's go back to what I said about what if you have density that is not uniform. So here we have a stick, and I'm just going to kind of, I know it's a rough sketch, but we're going to try to emphasize that one end of the stick is obviously more dense than the other. Okay, now the actual thickness of the stick, if this was something that was actually existing, you may not even notice a physical difference between one end of the stick and the other. Okay, what you might notice is that maybe one end of the stick is the same in dimensional size, but it has a different material, so its density is greater. Either way, we're saying in this stick that the density is not uniform. We'll say it to where at one end of the stick, it has a density of lambda 0, just some initial density, And at the opposite end of the stick, it's got twice that density. Okay, and then we're going to oversimplify that a little bit to say that it's a linear increase from one end to the next. So we increase our density linearly from lambda 0 out to 2 lambda 0. Okay, so if it's a linear increase, then we can write that the density is equal to mx plus b, because that's a linear equation, right? Now, we know this equation from graphs. M represents the slope. It's the rate of change. Well, in this case, we can calculate that rate of change by looking at the change in density over the change in x, because that's exactly how you find the slope. So the final density was twice the original, so 2 lambda 0 minus lambda 0. And the change in x is just from one end of the stick to the other, which we'll call the length. So if I work this out, I get that this slope value is lambda 0 over L. Okay, now x is my variable that's changing as I go along the stick, so that stays. And then b represents, on a graph, it's your slope-intercept. And in the equation, it's whatever the initial density is, which we already said on the left end of the stick, the initial density is lambda 0. Okay, what we've established then is a formula to talk about the density changing linearly along this stick. Now, in some problems, you'll be given the density function, so you won't have to do this kind of steps that we've done here. But I've seen a problem like this on the AP exam, where all it said was the density increased linearly from one end to the next, and you had to develop the equation yourself. So that's why I did this example. Okay, so now we're trying to find the center of mass. So we're going to write out the formula. Since it's a varying density one, we have to use the integral-based density. So on the top, we've got the integral of x dm, and on the bottom, we're going to do the integral of dm. Okay, now we can't quickly say on the bottom that the integral of dm is just the total mass, and you'll see why. I mean, it's true that the integral of dm is big M, but we're going to keep it like this just for now. Okay, so what I need to do first is I need something to plug in for dm. Okay, so remember we said before that the density is equal to dm over dx. So it follows then that dm is equal to the density times dx. Now you'll notice that in this problem, I kept the lambda in there. In the previous problem, we were able to get rid of lambda. Okay, we put in big M over big L. Can't do that here because it's not uniform density. So the ratios are not going to be equal. Okay, so that's the best I can come up with. All right, but we have a formula for the density. So that means that dm is whatever that formula was, which is lambda 0 over L times x plus lambda 0, and all of that times dx. So this is what I'm going to plug in to my integral function. So on the top, I've got the integral of x times the density function, dx. And on the bottom, it is the density function times dx. So I've got two integrals to evaluate here. Okay, both of them are going to have the same limits though, because we're integrating over x. And so from the left end of the stick, which is 0, all the way to the right end of the stick, which is L. Okay, so let's go ahead and calculate these out. So we're going to do the first one on top. Okay, now first thing I'm going to want to do is put that x inside, right? Distribute it out. So I've got integral of 0 to L, and this would be lambda 0 over L times x squared plus lambda 0 times x. Okay, and then on the bottom, nothing really has to change with that one. Okay, and again, you can solve the top or the bottom first, whichever one you want to do. So I'm just focusing on the top, which is why I didn't change out the bottom just yet. So let's go ahead and solve the top. So we're taking an antiderivative. So lambda 0 and L are all constants. So nothing's going to change with those. So this is going to be lambda 0 over L. Okay, then take the antiderivative of x squared. So that's going to be 1/3 x cubed. Then you've got plus lambda 0x, which means that's going to be lambda 0 over 2 times x squared. Okay, we've got to evaluate this whole thing from 0 to L. On the bottom, we're doing an antiderivative of this, so that's going to be lambda 0 over L times 1/2 x squared plus lambda 0 times x. And again, from 0 to L. All right, so let's plug in the upper limit for the top equation. So that's lambda 0 over L times 1/3 L cubed plus lambda 0 over 2 times L squared. Now, if I plug in 0, the whole thing's just going to be 0, so we're going to ignore that one. Then on the bottom, I have lambda 0 over L times 1/2 L squared plus lambda 0 times L. And again, if I plug in 0, everything's going to go away. So now all I have to do is combine like terms. So let's see, on the top, you'll see that the first term, one of these L's is going to cancel with one of the others, so it becomes an L squared. Well, now I've got like terms. I've got, let's see, let's write this out a little bit better. I've got lambda 0 over 3 times L plus lambda 0 over 2 times, L squareds. Sorry. Then on the bottom, one of the L's is going to cancel in this first term. And I'm left with lambda over 2 times L plus lambda times L. Okay, so combine like terms. So 1/3 plus 1/2 will be 5/6. So that would be 5/6 of lambda times L squared. Then on the bottom, I've got half of lambda L plus 1 lambda L, so that would be 3/2 lambda 0 times L. Okay, you can see here we're going to do some algebra. The lambdas are going to go away. 1L is going to cancel. And then if we divide these fractions, we're really multiplying by the reciprocal. So let's see, that's going to be 5/9 of the length, meaning the center of mass is just beyond the middle of the length of the rod. Now, I recommend that you redo that problem as much as possible because it is a challenge problem, and you may not see enough of the practices in the homework because it's not a skill I really want to beat into you, but I definitely want you to practice this. So start this problem over from scratch and do it over and over and over again until all the steps become obvious. All right, now one of the more interesting things of center of mass is when we look at the motion of the center of mass.
Okay, so if we have a system, say a box or a car moving with some speed and another box moving with some speed, now they're going to come in and collide. Well, we can find the x center of mass of this system, okay, just doing the normal way. But what if we looked at how that position's changing with time? Well, position over time is simply velocity. So this would tell us the velocity of the center of mass is equal to the mass times its velocity plus mass b times its velocity over the total mass. And that would tell us how the center of mass of the system is moving. Well, more importantly, when you're looking at a system of objects, ask yourself if there is a net force acting on the center of mass. So this will help you determine more about what the center of mass is doing for this system. Okay? Because if there's no forces on the center of mass, well, an object at rest stays at rest. So the center of mass was at rest, it'll stay at rest. For example, let's imagine we've got like a river or lake, and we have a boat on the lake. And on that boat we have two people. So let's see, we want to put one of them at one end of the boat. We'll have the other one at the other end of the boat. Okay, and we'll give the boat some dimensions. We'll say, well, first the person on the left is 60 kilograms. Person on the right we'll say is 70 kilograms. The mass of the boat is 100 kilograms. And we'll say the length is about 3 meters. So now if the whole system's at rest, okay, let's find where the center of mass is. So we do this in the usual way. We'll pick the first person, the 60 kilogram person, to be at the origin. That'll be mass 1. Mass 2 is the 70 kilogram person, and mass 3 is the boat. Let me write those up here. So you got 60 kilograms at the origin plus 70 kilograms at 3 meters. Then we also have the 100 kilogram boat, and since if it's uniform, its center of mass will be right in the middle at 1.5 centimeters, or excuse me, 1.5 meters. And then the total mass is 60 plus 70 plus 100. Okay, so we'll crunch all this out and we'll find that the center of mass is located at, so 360 divided by 230 gives us 1.57 meters from the left end. Okay, so center mass problem, same problem we've been doing. But now let's ask a different question. So what if that person on the left started walking towards the person on the right? So once they've reached the right end of the boat, how far has the boat moved in the water? Now you might ask, well, why does the boat move? Well, since the center of mass had no net force on it, the center of mass location, this dashed line, is fixed in space. So if I distribute weight elsewhere on the boat, the whole system has to move so that the center of mass line we drew in space does not move. Now, I know that sounds confusing, okay, but the whole point is the center of mass is a reference point in space, and that point is fixed. Nothing is acting on it. So if the person moves, then the boat will have to move to compensate for that shift in mass so that the center of mass stays the same. So how far does the boat move if child 1 walks to the other end of the boat? So the way to do this is, well, once the child's on the other end of the boat, what is the new center of mass? Again, the mass has shifted, so where from the left end of the boat would be the new center of mass? Okay, so 60 kilograms is at 3 meters, but the 70 kilogram kid is also at 3 meters, and the boat is still a center of mass in the middle. So now we solve for the new center of mass, and so let's see, this is the one I was thinking of earlier. So 180 plus 210 plus 150 divided by 230 gives us a new center of mass of 2.35 meters. So let's draw that on the boat. Now this means that that green line is the new center of mass, and the boat is going to move so that the green line lines up with the black line. Okay, when that person starts walking, that black line is fixed in space. So the new green line has to move to match up to the black line. So if we draw kind of a quick sketch of that, the idea is the boat moves to the left so that the green line gets dragged over to the black line. Okay, so I know that sounds weird, but I've got another video attached to this for us to watch. So you'll notice in this case, you've got a boat or a surfboard with a kid standing on top of it. Now, the little kid in the water, that's the center of mass. Notice that the center of mass is fixed. So as the kid starts walking, what do you notice the surfboard doing? The surfboard moves so that whatever the new center of mass of the system is, it lines up with that fixed position in the water.